that is correct. 444. This is still under the phylum Arthropoda. We just came out of dealing with several of the crayfish and crabs and lobsters and that particular group of arthropods, and now we're leading really to the largest class of arthropods, is what this chapter is primarily about. And in fact, it's the largest class of animals that we know, and it's class Insecta. Those old insects. We already decided that we really had to have them. We'd love to eradicate a lot of them. And not all insects are bad insects. That's against popular belief. Most people's like, just like the spiders, a dead insect's a good insect, a dead spider's a good spider. Not true. There's a lot of good insects out there. The number one pollinator of all time is bees. They pollinate billions of dollars of crops. Insects in general, multi-billion dollars worth of crops every year. So we've got to have them. So chapter 21 is kind of where we're at. And they start off telling you a little bit of background, talking about the staggering economic loss that insects cost us, yet we have to have it. So kind of the evil comes with the good kind of deal. Starting on page 446. 446, we'll just start with class Insecta. And the study of insects is entomology. And believe it or not, that's actually a pretty good field to go into. I know some students have come out of here and really not knowing what they wanted to study. They went on to OSU and ended up studying entomology. And then one went into environmental science with an entomology degree, and the other went into veterinary medicine with an entomology degree. And they loved it. So it's something unique, and there's jobs out there with entomology degrees. So we're studying insects, and that is entomology. Insects do differ from other arthropods in having some unique mouth parts, some for sucking, some for cutting and tearing, and just kind of a variety of mouth parts for every type of food out there for them to eat, which is about everything. There's an insect eating everything, but none of them compete with one another. Is that not crazy? That's why there's so stinking many of them. But they usually have two pair of wings. And we'll find that 96% of insects fly. Now, flies have smaller, more frail wings than a beetle does, but they still have two pair of wings. Now, as far as distribution, where do you think you'll find insects?
Water.
That's just one of many places. In fact, we could just probably continue a list up here. Anywhere life exists, you're going to find an insect, most likely. There may be some extreme conditions, you'd find limited numbers, but I still think if you dug deep enough, you're going to find some insects. They list mountaintops to forest, to freshwater, to soil, to marshes, salt marshes, sandy beaches, wastelands. I mean, it just continues. External form and function. The insect tagmata comprise of head, thorax, and abdomen. And this week in lab, we're gonna dissect probably a crayfish and a grasshopper. Next week we'll dissect a fish and a shark, because we're gonna get into the fish chapter today. We all got excited about a shark. The head usually bears a relatively large compound eye, a pair of antennae, and three ocella, which really two true eyes and one eye spot. Ocella are just in reference to eye spots. Mouth parts formed from specially hardened cuticle typically consist of a labrum, a pair of each mandibles and maxillae and labium, and a tongue-like hypopharynx. Kind of depends on the insect if they have the hypopharynx or not. The picture 447 is a good reference grasshopper picture for lab this week when we get to it. So kind of a general idea of the makeup of insects as far as external form and function. Now we want to move on to 449, and they'll tell us that the insects do have the power of flight, most of them anyway. I'm telling you that 96% of them do have the power of flight. Two pair of wings. Wings may be thin and membranous like you'd find on a fly, or they could be very thick and horny like you'd find on a beetle. So there's quite a variation in the kind of wings. Here's the two muscles involved in flight for insects though. This is highly scientific terminology. A direct flight muscle and an indirect flight muscle. There's your two muscle terminologies for insects. Those are on page 450. Direct and indirect flight muscles. Obviously, scientifically minded there. Internal form and function. Nutrition. The digestive system kind of laid out kind of like a bird a little bit. Has a crop. There's a little bit of digestion going on in the crop with insects where there's not with birds, but mainly for storage. There's no absorption of food molecules here in the crop. And then it goes on to a gizzard where it grinds it on up, just kind of like a bird. A midgut, which consists of a stomach and gastric ceca, and a hindgut, intestine, rectum, and anus. So, in essence, what we have here is a combined reproductive system that have components of a bird, which birds don't have stomachs, their gizzard's it, and then components of vertebrates, which do have stomachs. So, kind of a unique setup here. Most insects feed on plant juices and plant tissues, so most insects would fall in the classification of being herbivorous. They'd be herbivores. There are some that are saprozoic, that would basically absorb or lap up their food sources. And there are some insects predaceous, and a lot of those insects are good insects for us. They're predaceous on the bad insects. So they're out there as predators. The praying mantis would be a great example of that. There's smaller ones like a ladybug, ladybird beetles they call them. They're predaceous. They're out there eating aphids and very small, almost microscopic organisms we can't see that's doing serious destruction to our plants. Lacewings is another one. There's another bug out there called an assassin bug. I told the class yesterday, every now and then I get a brain wave. It usually consists of a lot of work on my part, so I think about it twice, so if I'm going to do it or not. But this is really something that I'm looking into doing. I'm going to get with the other zoo teachers and see what they think about it. But is it not important for us to recognize a good insect from a bad insect? One that causes destruction to one that actually helps us? Well, it would be nice to look at that and say, well, that one's good and that one's bad, right? So what I'm looking at doing, and I don't know if I'll get it done this semester or not, because I'm always coming up with brain waves. When they hit me, it sets me back. I'm not used to them very often. But what I'm looking at doing is just looking them up online, maybe printing photographs with names, and laying them out, and that being part of a lab. As you identify this, you have to go look this insect up as a good insect or a bad insect by researching these insects. So it takes a little time on your part as well, but at the same time, if you have a flower garden, or if you have a real garden, or if you just happen to be walking down the sidewalk and see an insect, you might have an idea if that's a good one or a bad one. Now, are all beetles bad? Are beetles even bad? They're not going to attack you and tear your hair off your head, are they? I don't know, depends on which beetle it is. Some of them's big and ugly, would you agree with that? Do you know what a beetle is? Okay. I'm not getting a lot of response here today, so well, I mean, there's like dung beetles. You think dung beetle, that's a crappy little beetle. I'm glad y'all's waking up to get the puns today. Dung beetles are good. They show a sign of soil fertility. But a lot of people don't know a dung beetle from the larval stage of whatever kind of beetle. There's I'm brain dead now, I can't think of any other names of beetles, but a dung beetle, their purpose is to scatter manure. I mean, basically they're going to roll up a pile of manure, shove it down the hole where they laid their eggs, so when their larva hatches, they have manure to eat on, and when they eat their way out, they're ready to transpose into the next stage and ready to go on. So that's the purpose of dung beetles. You know what the number one killer of dung beetles is? Cars. They don't cross the road fast enough, and that's not a joke, that's the truth. So most people don't see dung beetles around unless you're out there, I guess, playing around in dung, see if they're out there. But here you'll see these two little beetles rolling a little ball of crap across the road. What do? We want to screech on the brakes, or we're going so fast we didn't see them, did we? That's what happens. We just wipe them out because they can't get across the road fast enough. But I think it's important that we do recognize good ones from bad ones, and we may not get them all. But if we can have a general idea of what's in this area, what's good and what's bad, the next time you have an insect problem in your garden, you don't just go out there with some massive insecticide and kill them all. I mean, you don't want to kill the good ones. You want to encourage those, kill the bad ones. But ultimately, we see, oh, there's a little plant damage there. You see this little bug flying away, and say, oh, there it is. Well, that was probably a little lacewing that was there eating the aphids that was doing the plant damage. So you swat him down and kill him. Boy, I got him. You just killed the good one. And it's be like the Army turning around on us, killing all us off. We're the good guys. So, what do you think about that idea? Do a little insect research? You know, yes, you like it? Well, we have one person ready to work. Thank you very much. I won't work on that though. But anyway, back to the nutrition. Herbivorous, some predaceous, some are parasitic. Obviously those that have parasitic habits are probably not necessarily good insects, unless there's a handful that parasitize bad insects. How about that? That's a pretty good idea. There's a tomato hornworm. I believe if you look on the next page, there's a tomato hornworm, which is the larval stage of the American sphinx moth. You think a moth eats tomato plants? No, what this larval stage of the sphinx moth does. And so she goes and finds a nice healthy tomato plant, lays not one egg but several eggs. These little hornworms hatch and commence to eating the tomato plant, and man, can they devastate a tomato plant. Well, you look at the next picture and you see, ooh, that tomato hornworm's growing hair. Those are eggs of a wasp that's fixing to parasitize the worm. As soon as the eggs hatch, the larval stage of the wasp will eat the worm, and then it's ready to go to the next stage. You think the wasp will eat a worm that big? No, but the larva will. See, that's why there's so stinking many insects. There's no competition among them. They're always eating something different. At each stage, they're eating something different. Have anybody ever seen one of these hornworms in real life? I should have brought one up here. I pulled one off a tomato plant yesterday. He was a monster. A lot of times I throw him in the chicken yard, and the chickens look at him and take off the other way. That's how big and ugly they are. Think, well, that'll be a healthy meal for a chicken. They take off like a chicken. Imagine that. Well, other things, parasitize. Then you have those with sucking mouth parts, like a mosquito. Stick a probe in you and drain you. That's what they're good at. And then you get over on 452, well, they actually mentioned, I think, stylettes on the last page. That's what an aphid would have. An aphid would stick its stylet to the back side of a leaf and start draining the food of the leaf, which is called phloem. And how they actually figured out what was in the leaf was by way of aphids. A researcher was trying to figure out, what's those aphids eating in a leaf? What's so nutritious here? So he actually took a can of ether and he sprayed the aphids, which kind of froze them right there in one spot, killed them off, and then he took small tweezers and they broke off the stylet that was stuck out in it, and they left it stuck in the plant. And then the plant juices started seeping up out of the stylets, and they started researching plant juices and said, well, that's plant food. I mean, that's like blood in our veins to plants. So that's going around, an aphid would be a bloodsucker to a plant like a mosquito is to us. That's what it is. So moving on over to the next page, 452 there, we have sponging and lapping mouth parts. That would be a nasty fly, right? And chewing mouth parts, a grasshopper. They'll eat virtually any kind of plant, and people have claimed they've eaten the screens off their windows. I mean, that's how bad they can be sometimes. Circulation is a hemolymph. It doesn't serve the same purpose as our blood would. Our blood carries a lot of oxygen. Theirs do consist of some plasma and amoebocytes, but little role in oxygen carrying. The gas exchange is the same thing we'd said in an earlier chapter. It is a tracheal system. A tracheal system is very efficient because it's a direct airflow system straight to the tissues, through the spiracles around the abdomen. We talked about the swelling and shrinking of the abdomen. When it swells up, air rushes in, goes to where it's going. When it shrinks, we push air back out. All right. 454, excretion and water balance. And most of these insects, class Insecta, you'll find Malpighian tubules. Malpighian tubules. As far as sense organs go, they say that they have pretty well developed sense organs. In fact, they'll go on and say that including mechanical, auditory, chemical, visual, and other stimuli, they can pick them up some way, somehow. It may be ground vibration, but they can pick it up. They may not see something specific, but they can catch movement. Yeah, it's not great compared to ours, but pretty good. There's a lot of them for a reason. Now, one of their things is chemical senses. You ever wondered how a mosquito could spot you a mile away and hunt you down? Well, you know, there's all kinds of insect deterrents out there that we buy. Deep Woods Off was one that was out for years, and I believe it had in it a substance called DEET. You ever heard of DEET?
75%.
Is that what it is? 75% DEET? Well, here's how DEET works. These artificial repellents and attractants. What happens is there's an increase in carbon dioxide concentration that would happen, and say if somebody walking through the forest, say you left your truck going to a tree stand, okay? By the time you get to your tree stand, you may be sweating a little bit, probably breathing just a little bit heavier, depends on how far you walked, but there's a sense of more body heat, and you're giving off carbon dioxide. That's what the mosquito picks up, okay? So because this is put out in extra amounts, the mosquito picks it up and begins flying, and then focuses and follows this agent to warmth and moisture are the main cues. Once it finds its host, then obviously it latches into the blood. What DEET does is block the mosquito's ability to sense lactic acid, thus preventing host location. Does it work all the time? No. It's like, let's put some more on sometimes.
What about the candles that you put out?
I think they're a rip-off.
I mean, but they stink. What's that? What's that do?
Just to make you,
That's what I think.
it makes you think that it's working because it stinks. I think it attracts mosquitoes myself.
I don't like it.
What are they, citronella? Is that what it's called,
It's in your
citronella
lungs.
candles? Yeah, well, they just citronellaed your pocketbook. Now, most insects have compound eyes. There are a few with simple eyes, so they list both of those here. Most all of them we're familiar with would have compound eyes. It says a bee can distinguish colors, but its sensitivity begins in ultraviolet range, which human eyes cannot even see. Although uniform in color to our perceptions, bee-pollinated flowers often have petals with lines and angular shapes that differ in ultraviolet light absorption and reflection. So, bees typically like brightly colored flowers, but they can see components of that flower we can't because of a different light wave that they pick up. Reproduction, parthenogenesis is fairly common in a lot of insects. Parthenogenesis literally means virgin origin. The example of this would be a queen bee chooses to fertilize her eggs or not. If she fertilizes her eggs, she has diploid females. If she does not fertilize her eggs, she has haploid males. And that's her choice. But we still have living offspring any way you look at it. So that's considered parthenogenesis. And not overly common, but it happens. And they mention the queen bee. Now a lot of the like grasshoppers and crickets, they'll have internal fertilization and lay eggs, which puts them in the oviparous category. And they'll lay a lot of eggs. And those eggs a lot of times will sit there till next year and hatch out, and that's where we get all the grasshoppers for the next year. So oviparous would be very common in a lot of insects. Parthenogenesis would be less common, but it does happen in a lot of insects. Metamorphosis and growth. This metamorphosis process that we talked about is the reason there is so many insects. They listed it at the beginning of the first arthropod chapter, but in truth it was basically in reference to this chapter right here more than anything else. Insects change in form undergoing metamorphosis during this period, but they must undergo a series of molts to grow, and each stage between molts is called an instar. So they don't just go from hatching an egg to whatever they are, they go to the larval stage, to a pupa stage, and each one of these stages has an instar stage between it before it reaches the next stage. And there may be 5 stages, there may be 3 stages, there may be 6 or 7 stages before they reach that final adult reproductive stage. And each time inside of that would be an instar in between each one of those. Transformation, for instance, of a hickory horned devil caterpillar into a beautiful royal walnut moth represents an astonishing morphological change. And I don't tell you how many there is because each one differs, but there is several instar stages to get there. 88% of insects go through complete metamorphosis though. 88% go through some kind of major complete metamorphosis. Each stage functions without competition with the other stage. These are things I've been saying all along. For the larvae often live off entirely different surroundings and eat different foods from adults. The worm-like larvae, which usually have chewing mouth parts, are known as caterpillars, maggots, bagworms, fuzzy worms, and grubs. These little big white grubs you might see in the spring of the year, they end up being one of those beetles that's humming around your lights outside your door at night. That's what they end up being. That's a larval stage to this little ugly beetle. But they fly. They've got the wings and they're flying. Now they mentioned larval molting persists as long as the juvenile hormone from the original stage is still there, flowing through the hemolymph. Now, what we've done is we have mimicked juvenile hormone. We found that if you actually, even on an adult, if you sprayed juvenile hormone on an adult and got enough in the system, that adult cannot reproduce. So from this idea alone, we basically have figured out how to eradicate insects as a whole. And then we backed up a step and took a look at it. Do we really need to do that? And the answer is no. So what we have is a juvenile hormone that allows them to go through these molts, metamorphic molts, instar stages, and then in each one of those, you will there's no reproduction because the juvenile hormone does not allow reproduction. As long as they're juvenile, they cannot reach adulthood. Through this process of molting, there's a hormone called ecdysone. It's EC. Something like that. I may be off a little bit. Maybe something like that. We'll see it in a minute. Ecdysone is the molting hormone, and the process of molting, going to the next stage, is called ecdysis. I think that's with a Y, so it's probably ecdysone. Ecdysis. Okay? Moving on over 461, and figure 2129 shows you your little dung beetles at work. Oh, they're working hard to get across the road. This happens to be an African dung beetle, but I guess if it was in Oklahoma, it'd be an Oklahoman dung beetle. But they got a little bit, ours don't quite have the shiny coat on it that the African dung beetle does, but they're doing the same job, getting the same thing done. Insect communication, behavior and communication. They can communicate many different ways. Now, insects that make noise have the ability to hear, but not all insects make noise. Now, there's exceptions to the rule. For instance, it's the male cricket's the only one that really makes noise when it comes to crickets. But what good would it do the male cricket to make noise if the female didn't have ears to hear? Don't you think his noise is going to be headed her direction to talk her into coming over here? It absolutely is. But one thing, if you ever learn cricket lingo, which I don't have any idea what cricket lingo is, but I can tell you this. Somebody has figured it out because they say that a male cricket can never tell a lie in his lingo because it's instinctive lingo. He's programmed to say only certain things. He cannot even give her a warning if he sees her coming and sees danger. He cannot change his message. His message is where I'm at, what species I am. Basically, I'm talking because I'm the dominant male. Otherwise, I would shush because somebody's already beat me up, kind of deal. So he can't ever stray from the original message. And it's very simple. She's gonna end up choosing, but his message is simple, and at least she can find a location to make a choice. So, male crickets can never tell a lie. Would that hold true with all males? Oh, I got a quick answer over here, of course, from a female. Well, I just thought I'd ask. Didn't have to be that harsh about it. And then there's chemical messengers. Now, this is one of my favorite. Chemical messages. It depends on the species, what type of chemicals, but in general, they use chemicals called pheromones. And here's a good example. It's one of my favorite stories in chapter 36. When we get over to 36 and I start telling this story, y'all stop me before I tell it again, because I'll get over there and tell it again. But that whole chapter is animal behavior. And they talk about communication by way of pheromones. And the pheromone communication, let's take moths for instance. A particular species of moth, when the female is ready to mate, she gives off a pheromone called bombacol. It'd be in essence the equivalent to the highest quality perfume you could find. I mean, it travels and it's got a message with it. I'm ready. Okay? So, the male that would have the most sensitive receptors to bombacol would be probably the male that would mate with her. Would you agree? And it makes sense because they want to produce offspring that has sensitivity to this so they could continue the species. If it's a male with less sensitivity, then we don't need more offspring with less sensitivity. The species may eventually die out. So let's say, for instance, a female is giving off bombacol. And off in the distance, and downwind, of course, there's two male moths goofing off, probably absolutely doing nothing. And one male moth just, poof, he's gone. And the other one's probably communicating with him, and he's just like you and I'm talking and you walk off kind of deal. And he's saying, well, that was rude. My buddy just took off. No question, what's up with that? You know, and he's kind of fussing at himself a little bit, and all of a sudden it dawns on him, bombacol. He knows where his buddy went. So he's following the trail of bombacol, only to get there too late. When he gets there, his buddy's over smoking a cigarette. See? So his buddy gets there and reproduces and dies of cancer later. You gotta get off the cigarettes. That could mess up sensitivity. But needless to say, you're continuing genetics of the species that is more sensitive, therefore they're the ones that will continue the species. It's survival of the fittest. First come, first serve in the animal kingdom. If you get left behind, sorry, you just get left behind. There are no friends when it comes to reproduction in the animal kingdom, unfortunately. Sound production, we've mentioned crickets, and they mentioned male crickets scrape modified edges of their forewings together. And chapter 36 will elaborate more on the crickets. And there's other forms of tactile communication. And then the visual signals. Has anybody not ever went out in the summer and caught fireflies? I mean, as kids, have you never caught a firefly? Oh my gosh, she's not lived. Check her pulse. I don't think she's alive. Were you raised in this? Oh, okay, that explains it. Because if you run around with any of us growing up, you'd be the biggest hick ever. Because we'd have a jar of fireflies dead sitting around the house somewhere because we forgot to turn them loose after we caught them. But it's pretty cool to see them all lighting up the sky. At certain times of year, there's really a bunch of them. Well, that's ways of communication. The males and the females are communicating back and forth, and the female sends a signal, the male sends a signal, and their signals connect, and next thing you know, reproduction occurs. But there are some females of other species have learned the language of another species. And so what she does is get involved with the other species, starts flashing this foreign language around. She attracts the male of the other species not to reproduce. They're not going to cross the species. She's hungry. She just don't want to eat her own species. She wants to eat another species. Yeah, she gobbles him right up. There's a picture on the next page. She's one mean hombre. Look how big she is. That's not even right. By the time he gets here and figures out, ooh, this is one big mama, it's too late. Yep, But they mimic that's really unique, because she learned a new language. That's not supposed to happen, because these are supposed to be species-specific languages. They learned the other language. So there's bioluminescence. And they mentioned it in the reading as well. Now, the next topic here is social behavior, which we've been kind of covering some of that as we go as well. Honeybees, they talk about have evolved a very efficient system of communication. Again, in chapter 36, the honeybees, this is amazing. And whoever sat around and figured all this stuff out had a lot of time on their hands, but that's probably getting paid for. But everything like a scout will go out to honeybees, come back with probably pollen on its legs or covered with pollen, and well, that just excites everybody at the hive. And then the scout will start doing either waggle dances or round dances or a combination of both on the hive. And the direction of the dances is always directly correlated with the verticality of the hive, which is coordinated to where the sun is, the direction of the sun. And so they always know if she's 30 degrees to the right of the vertical, then the food is 30 degrees to the right of the sun. So they know direction and how often they do it. They do the dances or the runs. There's a time frame there of how many yards, feet, whatever, distance. There's a distance information in it as well. And if there's a lot of food out there, they really don't dance a whole lot. They basically say, hey, there's food out there, get your butt out of the hive and go find something. Now everything they do, they repeat. They do it over and over, and I think that's for the slow ones. They need them to do something. So that everybody else is gone. What are you still doing here? Well, can you do that one more time? Maybe they just like to watch the dances, I don't know. But distance and direct, now if there's not a lot of food available, dancing is intense because they cannot mess up. When they send them a direction, you've got to come back with something. So the scout has really worked hard, and he'll work hard to tell them exactly where the food source is. So that's another unique thing we'll talk about chapter 36 as well. I actually wrote a paper on that one time, and it was scary. 463, insects and human welfare. So the bottom line in this whole deal here is they do millions of dollars of crop damage, and they pollinate billions of dollars of crop. Okay, millions and billions. There's enough in between there to make them worth being around. All right, we've got to have them. They named several of them predaceous insects. Here's some. These are good ones. Predaceous insects are good ones. Tiger beetles, aphid lions, ant lions, praying mantids. That's one ugly insect, isn't it? Wouldn't you like one of those crawling up? Oh, they're probably just picking other insects off of you didn't know you had. Ladybug beetles, everybody likes a ladybug. They destroy harmful insects. In turn, insects serve as important sources of food for many other animals. Parasitoid insects are very important in controlling populations of many harmful insects, like we saw the wasp laying eggs on the hornworm earlier. And nothing different than a fly laying eggs in a carcass, and the maggots eat the carcass. There's a purpose being served there. And of course, the good things, some of the other good insects produce, whether it be honey or beeswax or shellac, there's just tons of stuff that they do produce. Now, the harmful insects, here's quite a list. We have grasshoppers, chintz bugs, corn borers, boll weevils, grain weevils, San Jose scale, and hundreds of others. Nearly every cultivated crop has several insect pests. People expend enormous resources on all agricultural activities in forestry and in the food industry to counter insects and the damage they cause. Outbreaks of bark beetles or defoliators such as spruce budworms, hemlock woolly edelgids, I can't even pronounce that, and gypsy moths have caused tremendous economic losses and have become a major element in determining the composition of forest in the United States. They're literally wiping out certain species of trees, which means there's no more of that species, so another species will probably take its place, changing the whole makeup of a forest in some cases. Insects. Notice a lot of pine trees dying in this country. I'm sure some are drought stricken like the oaks, but there is a pine beetle that has been in this country for quite a while, and it's gradually taking out the pines. I mean, you'll see a whole grove just start, this one's dead, this one's dead, this one's dead. 10% of all arthropod species are parasitic insects. 10%. That's not a lot unless that whole 10% seems to be pursuing you. We have lice, blood-sucking flies, warble flies, bot flies. Now let me just back up a second. The warble flies, bot flies, no, not the bot flies, warble flies and mosquitoes, I think, is the two primary ones in the tundra. And when we get in the mammal chapter, it'll talk about those. The caribou make it to the tundra certain time of the year because only like a small time frame there, food sources are really high. So that they go there to have their calves and to gain some fat afterwards, and they have to leave. And they have to leave because those two insects alone suck a pint of blood a week per caribou. Now I saw a picture on the tundra of a caribou the other day, and behind it was just a fog. And what the fog was these insects after it. That's how crazy it is out there. Of course, I've said all along, the state bird of Alaska is a mosquito. If you've never been to Alaska, if you ever go and see a mosquito, you will agree. You'll text me and say, I believe it. So the mosquitoes are listed as part of the blood-sucking flies, warble flies, bot flies, mosquitoes, they're all there. Hundreds of millions of people each year, causing millions of deaths. Mosquitoes also transmit yellow fever, lymphatic filarias. Fleas carry plague, which in times of history kills significant portions of the human population. House flies are vectors of typhoid, as are lice for typhus fever. Tsetse flies carry an African sleeping sickness, and blood-sucking bugs carries or transmit Chagas disease. Now, Chagas disease, when they say blood-sucking bugs, that is actually carried by a bug called the kissing bug. The kissing bug tends to live in the homes of wood rats. And if you have kissing bugs in your house, you better start looking for a wood rat somewhere. Wood rats typically build big mounds out. But anyway, these kissing bugs will sneak up on you at night while you're asleep. And they love the soft tissue of the lips. That's why they call it kissing bug. And you don't even really know they do it. But that's how you get Chagas disease, which we don't hear of much in the United States. But it has been here. So beware of wood rats, I guess, would be the moral of that story. But from that, they also now are listing the West Nile virus, which I believe there has been 2 cases diagnosed in LaFleur County in the last 2 weeks. So I know there was 1 case in Poto carried by the mosquitoes. So West Nile virus first came out as an infection of horses, and then it transmitted over to humans. That's always a bad thing when viruses go different animals. That's not good at all. But this killed a few people already in Dallas. Usually older generation people, immune system's a little lower, but it's pretty damaging. West Nile virus is. So the tremendous destruction of food, clothing, and property by weevils, cockroaches, ants, clothes moths, termites, and carpet beetles. Just talking about those things give you the heebie-jeebies, don't they? I mean, when we think of insects, we think bad, but there's a lot of good out there to think about. Now, what is control? Control of insects. All right, you call a termite company and have them come out and spray some poison around. It helps. Do they kill good ones? Absolutely. They kill good ones as well as bad ones, but we're rolling the dice that there's more bad ones than good ones, and probably so. But boy, when you have a good one, you hate to kill it. Other means of control, tomato hornworm, for instance. You can sit there and look at that tomato plant all day, see the damage, and can never see the worm. I mean, he is so camouflaged. So a natural control for the tomato hornworm and cabbage looper and some other of these would be you'd go down to the co-op and you'd buy a little can of powder. It's about this big around, called dipple. And dipple has a bacteria in it called Bacillus thuringiensis. Bacillus thuringiensis is naturally occurring out in the soil. We're around it all day. In theory, I'm not telling you to go home and do this, but in theory, you could eat dipple and it not bother you. You can't say that about the worm. So you spread the little dipple on the tomato plant. That night, the worm comes out and eats a little dipple. The bacteria, Bacillus thuringiensis, starts eating the worm inside out. Within 48 hours, he'll be barely hanging or maybe even not on the plant and black as coal. They kill him. And there's a Bacillus thuringiensis for hornworms. There's a Bacillus thuringiensis for army worms, and they really got them specialized out there. Now that's a natural defense mechanism. Yeah, we could put together some malathion spray and just hammer the whole garden and kill good, bad, and ugly. But that's really not what we're out here to do, is to do that. But those are some ways to do this. And they list broad spectrum insecticides. Not a good option. Sometimes it's your only option, but it's not a good first option. All right, I think that takes us through that chapter and takes us over to chapter 23. Not a lot to say about chapter 23. We want to go straight to page 504. Straight to page 504 in chapter 23, because we want to look, this is the only thing we need out of this chapter. We want to look at the 5 chordate hallmarks. So what we've done is we've been in invertebrates since chapter 9. 9, 10, we've been talking about worms, protozoans, all the way up to the arthropods. These are all invertebrates. They have no vertebrae, no bony structure, all exoskeleton, or not even that in case a lot of the worms, they have no structure to them at all. It's what's called a flexible skeleton or a hydrostatic skeleton is what the book likes to use. Now we're beginning into the chordates. This is getting closer to us each time, in case you hadn't noticed. 5 chordate hallmarks, here they are. Notochord. Notochord sounds like your spinal cord, but it's not. Notochord is your spine. It is your backbone. The second one is the dorsal tubular nerve cord. Dorsal tubular nerve cord. That is your spinal cord. That is your spinal cord. Number 3, pharyngeal pouches or slits. Gill slits is another way. We don't have them and when we're born, but during embryonic development we do. And each slit, and I think there's 3, maybe 4 of them, specialize into something specific. And when we get, I believe it's chapter 7, which is on the final, that chapter will identify those in more detail. And then endostyle, which is a fairly new one they've thrown in here, and it is important. Endostyle is your thyroid gland, is what it is. Endostyle is thyroid, and then last, in which we don't have when we're born, is the post-anal tail. So we were tadpole-like at some point, so they say. This actually has gone pretty darn early in embryonic development, but we have documented it, it is there, and at some point anyway. So I think they use all these to fit everything we need to into this group. Not all of them fit us to a T, but we see characteristics at some point of these in embryonic development. Moving on over to 509, I want to point out a subphylum vertebrata, and they're trying to change this name. They have it in parentheses, the craniata. And all this is pointing out is that we can determine a head end. Would you agree that the roundworm, the Ascaris lumbricoids we cut up last week, it was kind of difficult to determine one end from the other? Well, we're getting into a group of animals now that you should be able to tell that that's the head and that's the tail. Okay, that's all that's referring, craniata. All right, page 513. So this chapter just did a slight introduction to chordates. The next chapter is the fishes. I know that's going to drive you nuts. I'll explain that in just a second. But we're going to look in the fishes chapter at superclass Agnatha, which is going to be hagfishes and lampreys, and superclass Gnathostomata, as well as class Chondroichthyes and class Actinopterygii, which they've changed the name of that. And they're always changing stuff. Class Actinopterygii used to be called Osteoichthyes. Osteo referring to bony structure, bony fish. second in number to insects. That's how many of them there are. Say, classification wise, class insect is number 1, number 2 in number, bony fish, Osteichthyes or Actinopterygii, however you want to look at that, but bony fish, number 2, okay? And then, that's the next chapter we're fixing to get into, and then the last 4 listed in this table, class Amphibia, class Reptilia, class Aves, and class Mammalia. Those 4 right there makes up our next test, which will be test 4, those 4 chapters. All right, from that, we're ready to get started in the fishes chapter. Does that bother you, me saying fishes? Like a small child that don't know what he's talking about up here? Does it bother you at all? No, not really? So everybody in your household says, oh, look, Mommy, I caught 14 fishes. That's just wrong. That's wrong English, is it not? Well, it is and it's not. Okay, if they bring in 14 crappie, he caught 14 fish. If he brought home 5 crappie, 5 bass, 5 catfish, he threw in a couple of gar, a couple of drum jumped on there, wasn't supposed to, you know, then he may have 6 different species of fishes. See what I'm saying? So it's not numbers, but it's different species is the reason we have a plural to the fishes. Now that I've got that clarified, we'll move on. Turn it over to page 520. The life of a fish is bound to its body form. Now the old saying, a fish out of water, well, throw us in water, it would be the same as a fish out of water. There's only a period of time we're gonna survive. After that, we're toast, because it's not our natural environment. So they're bound to their natural environment, is what it's saying. Fishes have excellent olfactory, visual senses, and lateral line system, which has an exquisite sensitivity to water current vibration, okay? If we look at this real close, fish have excellent olfactory and vision. If they didn't, we as humans are idiots. Go to Walmart and see how many scents you can spray on a lure. You ever think crawfish, shad? If you're fishing for catfish, how about some scent there? Stink bait number 1, stink bait number 2. Some of these baits stink, I'm telling you. All right, so maybe we are smarter than a fish. We know how to attract them in certain ways. What about colors? Does color make a difference? I think it does. Of course, if it didn't, we'd be stupid. We're just going to use this black plug. It doesn't matter. We can use it anywhere we want. Anywhere in the world, just use black plug to catch fish. It's not true. So they do have good, excellent olfactory and visual. Now this lateral line system, this is a sense of touch for them. How many of y'all have been fishing? Okay, good. I was hoping that was a high level of people. How many of y'all like to fish and would go again if somebody took you? That's even better. How many of y'all was fishing when you was little and that's the only time you went fishing? Okay, you didn't like it? How many times were you told, shh, be quiet, quit throwing stuff in the water, quit banging on the boat,
I wasn't really quiet.
sit down, be still, don't fall in the lake? How many times you heard that though, even after you went fishing several times? And you really didn't know why they was telling you that, but even now you tell, shh, will you be quiet? You keep rattling around the boat, you know, open up an ice chest in the boat, slam the lid. What'd you do that for? You know, aluminum boats, you just barely tap it. You know, just like sending off bells across. Now you know, now you're gonna know why you have to be quiet when you're fishing. Does voices travel across water? Now, have you ever stick your head underwater and try to hear somebody talking? You can hear it, can't make much out of it, but you can still hear it. I mean, understanding it, fish don't have to understand it. They just know there's something there. That's all they have to understand. So quietness is important. And this lateral line system is how they pick up that. They pick it up through vibrations in the water. And I mean they travel well in water. You ever stick your head underwater and click 2 rocks together? It's almost as loud as it's taking above water. You know, fish pick that up really fast. Let me give you a great example of this. Me and my brother-in-law, I have to tell off on my brother-in-law all the time. brother-in-law and I, we went down to the old riverbed at Worcester. Anybody familiar with that? And we had heard, boy, they was catching crappie down there. So, man, we're gonna go down there and snafu the crappie, right? But as soon as we pull up, they shut the gates off. That's always what happens to us. Oh, here comes Dwann and Clay. Let's shut the gates down. They're gonna try to catch fish today. Well, we pull in there, and it was a bad sight just to see us pulling in, and there was one other boat out there. That tells me nobody's catching anything. But we was down there, so we put our boat in anyway. We just had a little scamp. But we fished there a little bit. This other boat was in the best place, and we knew it. And it was a grandpa and a couple of kids. Well, this is cool. And every now and then you'd see them pull up a crappie. And I'm talking the kids are probably 8 to 12 in that range. And my brother-in-law and I, we was bored, so we decided we was gonna start catching gar. So we dropped our bobber down, and I don't remember what we had. Maybe we just had minnows or something, but we dropped it down and just on top of the water. And sometimes you can do this with nylon cord. You can fray it and throw it out there, and those gar hit it, get tangled in their teeth. But whatever we was doing, we was catching some gar. You know, you don't just lip them and bring them in the boat. So we had this little scamp. We was using ultralight tackle too, which made it last. We was out in the middle, so we could fight them, and they'd drag us around. We'd get it up to finally get them wore down. And if I had him caught, I'd pull him up to the boat. My brother-in-law, we had a little paddle about that big in the boat. My brother-in-law would whop, hit him upside the head, and then we'd take a pair of pliers and pop the hook and hit him. Whoop, whoop, whoop. You know, we'd kill him basically. So if he caught one, I'd take the paddle, whop, and I'd hit him upside the head. Same thing. Well, when just a little bit, we heard a racket over to the other boat. Looked over there, and one of these boys had hung into a monster gar. It's bigger than any of them that we'd caught. And this gar was cleaning house. Grandpa had about 10 poles out. You know how they are. They just line up poles all around the boat. Boy, he was pulling them in. He was trying to get out of the gar. He was just making a tangled mess over there. And these kids, boy, this is just hanging on. And Grandpa was trying to reel them in. And all of a sudden, we heard this noise. Bam! What in the world? One of those boys picked up the oar out of that boat, and that gar come by, he went, wham! He missed the gar and hit the boat. And Grandpa's like, what'd you do that for? I said, they were doing it. Man, we put that trolling motor in high gear. Dumb and Dumber was getting out of there. We got out. Grandpa just pulled the boat up on, his little flat bottom, but pulled it up on the bank, they got in the car, and he was mad. I mean, he was ranting and raving. Possibly even cursing those poor little kids. Man, I don't think there's any fish left in that entire riverbed when we got finished that day. But that, Grandpa knew what was happening. We scared every fish out there. Well, we were pretty precise in what we was doing. We had a fiberglass boat. We just popping them. He brings out a freaking 6-foot oar and hits the side of a metal boat. And Grandpa didn't see it coming. Man, that was funny, but I thought we was going to die over it. All right, moving from there on down to agnathans. The earliest vertebrates were an assemblage of jawless agnathans. This is on page 520. The agnathans are of two groups. Let me get this thing going here. It's already down. You have a handout. It's in the back of your notes, and it's a flow chart. So you can follow along on your flow chart. Put some notes in there if you will. But I gave you this flow chart at the beginning of the year. That's it right there. Classic agnathans, the big flow chart. You had it right there. And we're going to look at two species of agnathans here. One's called hagfish. That don't even sound good, does it? And the other one is called lampreys. Hagfish is where we're going to start. On the left-hand side of this, we see there's 65 species of hagfish, class Myxina. They tend to be of a sort of a scavenger fish. They're a hunter in some cases, but they're hunting dead or weakened prey. Mostly blind. They follow their sense of smell. They have a tremendous capability of smell because they like dead things. Dead things tend to smell. So they find dying or dead fish, and they bury themselves up in this fish. They find some orifice or some way to enter this fish, and as they enter it, they slime everything. That's what they're known for, is just disgusting amounts of slime. And when they slime something, nothing else wants anything to do with it, so they just marked it as their own. I mean, we need these kind of fish to an extent to kind of clean up the dead matter, but these are really disgusting little fish. So, renowned for their ability to generate enormous quantities of slime. So there's your general idea of hagfish. They like digging or burying inside their dead prey and sliming them while they're doing it, and nothing else is going to bother them in the process. Okay? So there's hagfish, class Myxina. The other jawless ignathan is the lamprey. There's only 22 species of lampreys, and about half of those species are the brook type, and they're non-parasitic. They cause very few problems at all. Most people don't even know they exist. And then the other half are parasitic. All must come to fresh water to reproduce, although some are considered to be anadromous, which they live their life out in sea and then come back to fresh water, and there's a small portion of those that live in fresh water their whole life. So lamprey's specialty, they're more of a parasitic fish. And as we look through here, it says all use fresh water to breed. Anadromous is the term. Adults die soon after spawning, kind of like a salmon situation. They come back, they spawn. It may take them 2 to 7 years to do that, but once they spawn, they're dead. They're going to die. Larvae grow slowly, 3 to 7 years before the larvae ever reach adult stage. And then I think the book says 1 to 2. I read in one place up to 7 years sometimes before they actually come back to spawn. And that would depend on if population numbers were way down, they'd spawn more often. If population numbers were up, they'd spawn less. So that just depends. Parasitic lampreys may migrate to sea or stay in fresh water, depends on which species. Adults live 1 to 2 years before spawning. Anadromous live 2 to 3 years. So it takes them a little longer. They're traveling further. They're going out to sea, they got to come back. It's a little longer travel. The small print down there talks about a problem that the Great Lakes had in the 1940s. Lampreys caused enormous damage to the fishing industry. And in this process, they didn't realize what was happening. And lake trout was like the #1 species of fish that was the moneymaker on the Great Lakes at that time. The #1 fish that was parasitized by lampreys was lake trout. And lampreys started just enormously increasing in numbers to the point they wiped out lake trout. And then they went to another species. And then they went to another species. The next thing you know, the fishing industry collapsed. There was nothing to fish for. These lakes were full of lampreys. The Fish and Game, and it took them about 20 years to recover this deal, about 15 to 20 years. The Fish and Game Department started studying the problem and coming up with solutions. And you know how they fixed it? They stocked more lampreys. They stocked more lampreys, but this is what they stocked. They raised lampreys in the fisheries, and when they put the lampreys in the lakes, they made sure that there were only males that they put in the lakes, and that all these males were sterilized before they were put in. Because they figured out that lampreys, female lampreys, will mate one time. That's it. They won't mate multiple times. They'll mate one time to one male, and that's it. So, and in fact, mosquitoes do the same thing. By the way, they're looking into that for mosquito control, is throwing out some male mosquitoes that's sterilized. So they put out these sterile males. Sterile males would mate with the females, and the eggs wouldn't hatch. And this went on for several years, and finally in the late 1950s, the fish, after of course they were hatching fish and putting fish back in the lake, trying to restock the lake and get things going back in the lake at the same time, within 15 to 20 years from the beginning of the problem, they finally saw the end of the problem starting to turn around. Now that's huge. You're talking about devastating to an industry. That was extremely huge. So there's your lampreys. Keep those in mind. Flow charts there to help you out on that. And that takes us now over to cartilaginous fish, which is on the right-hand side of 520. Does that show how much time I have left?
No, but you're at 59.
I don't know how much I go past that. So mark the cartilaginous fish. We'll stop there because I think that thing kills over just a little bit. And we'll pick pick up there next time.
Come here first.
Go ahead and kill that. Let's, you know, this is the last chapter before our next test. So we're looking at carbon